On the 15th of March 1944, the sky above Cambridge was bright and cold as steel. At 15,000 feet, the 8th Air Force's P-47 D-10 squadron flew in escort formation, their silver fuselages catching the weak sunlight through thin clouds. Captain Francis Gabreski pushed the throttle forward, watching the manifold pressure gauge flicker around 52 inHg, below the theoretical limit. He flipped the water injection switch, hoping the anti-detonation system would engage. Within seconds, the Pratt & Whitney R-2800 double wasp engine responded with a heavy roar, then choked, shuddered, and coughed violently. The manifold pressure needle dropped rapidly, from 65 to 52 inHg, as cylinder head temperature spiked. In his headset, pilots from other flights shouted, "Power loss, rough engine," panic signals rippling through the formation. According to the 8th Air Force Maintenance Section report, within 10 minutes, more than 200 P-47 D-10 aircraft simultaneously lost power. No enemy had fired a shot, yet the entire squadron silently fell from the sky like stricken machines. The newly praised anti-detonation system, once hailed as a technological breakthrough, had become an invisible menace. At 63 inHg manifold pressure, instead of boosting output, the engines were being destroyed from within. Pistons thrashed inside the cylinders, spark plugs burned out, and bearings melted within minutes. According to Republic Aviation's internal technical summary, at least 17 R-2800 engines suffered total failure that day. The R-2800's rated output was 2,000 horsepower, but when the water alcohol system was activated, power dropped to 1,600 HP, accompanied by vibration, black smoke, and erratic mechanical pounding. While pilots tried to throttle back to safe levels, the engines continued to explode in bursts. Post-sortie reports indicated that cylinder number 14 was often the first to crack under heat stress. Cylinder head temperatures exceeded 500 degrees Fahrenheit, and combustion pressures could reach 800 pounds per square inches, surpassing metallurgical limits. Beneath the wings, fragments of burning engines fell like iron dust, glinting in the sunlight above the sea of clouds. When Gabreski limped his aircraft back to RAF Steeple Morden, the ground crews had already received nearly 30 emergency signals. Some pilots had to belly land because there wasn't enough power to maintain altitude. Master Sergeant Mike Quirk, the chief mechanic, removed the cowling and immediately saw the familiar signs of detonation: scorched spark plug electrodes, holed pistons, cracked cylinder heads. He touched the still hot surface. The metal crackled faintly, the oil film reeked of burning. On the inspection board, he penciled a note. Cylinder detonation, non-random pattern. The engineers called the phenomenon auto-ignition, but in Quirk's eyes, it looked like a sickness born from the system itself. According to the 9th Air Force Technical Liaison Report, the maintenance stations at Debden, Boxted, and Lyon all reported the same results. Whenever the anti-detonation injection system was engaged, the engines destroyed themselves. Throughout the day, all squadrons were ordered to land, and escort missions were suspended indefinitely. The 8th Air Force, the symbol of American mechanical power, was momentarily paralyzed by the very technology it had trusted completely. At the command level, an emergency meeting was convened that night at Steeple Morden. In the briefing room, fluorescent light fell across the weary faces of pilots and mechanics. Gabreski's report lay at the center of the table, containing only one line. Water injection system caused severe engine roughness and power loss at 63 inches manifold pressure. System promotes detonation. The statement was short and emotionless, but it struck at the root of the problem. A system designed to protect the engine had become the very cause of its destruction. According to the Air Technical Service Command, the failure did not stem from mechanical design but from the chemical nature of the mixture. The system was fed with isopropyl alcohol mixed with distilled water at a 70/30 ratio, theoretically yielding an octane rating of 118 sufficient to prevent detonation. But under combat conditions, when combustion temperatures exceeded 2,200 degrees Fahrenheit, isopropyl broke down, forming pre-ignition compounds that triggered uncontrolled explosions. What was meant to be the antidote had become the catalyst of disaster. Technical officers described the issue as a mechanical paradox. The more precisely the system followed procedure, the more likely the engines were to fail. In subsequent records, many engineers compared the phenomenon to self-corrosion, a system consuming the very energy it generated until collapsing from within. The first cable sent from England to the US. Air Force Command at Wright Field opened with a chilling line. Catastrophic failure pattern observed across all units. Recommend full suspension of ADI operations. That night, Gabreski sat in the ready room, listening to the scattered sounds of engines being tested out on the runway. On the table lay a cold cup of coffee and a folded report, the paper creased with sweat. He knew that once the phrase, "System promotes detonation," was transmitted, it would not stop at the group level. It was the first indictment aimed at an entire industrial apparatus, convinced that every number was right. According to Major Harold Neely, engine evaluation officer at Wright Field, that day, physics didn't fail us. Our arrogance did. The numbers 63 in Hilling, 2,000 hops, 500 degrees Fahrenheit were not wrong, but the system's blind faith in them, as immutable laws, had turned the battlefield into a deadly laboratory. A week later, the image of P-47Ds lying motionless on the runways had become a silent emblem. Beneath the wings, mechanics brushed oil from exhaust pipes with grey rags as white smoke still curled from the cylinder mouths. In Quirk's technical journal, the final entry for March 15 was written in rough strokes, engines failing in sequence, one after another, like a system consuming itself. On a deeper level, that day's incident was more than a technical failure. It was a test of an organizational nature of how humans placed total faith in machines, procedures, and formulas, never suspecting that such faith could betray them. Everything built to protect had the potential to strike back. Like a biological organism gone awry, the 8th Air Force became a vast body biting into its own heart. In the decades that followed, engineers would look back on the 15th of March 1944 as a symbol of limitation. In the halls of the US Air Force Museum at Dayton, where black and white footage plays of pilots making emergency landings, the sound of metal clashing still echoes like the arrhythmic heartbeat of an entire industry. And on the dim screen, one hears Gabreski's voice again, low but resolute. The system failed us, because it thought it couldn't. And in that silence, the system devoured its own engines. 6 days after the Cambridge crisis, the American sky lay under a silent layer of grey clouds. In a conference room at Wright Field, Ohio, light filtered through frosted glass and spilled across a long table of dark wood. More than 20 engineers, generals, and industrial representatives gathered around the schematic of the Pratt & Whitney R2800 engine, with the tactical map of Europe spread before them. The wall clock read 8 a.m., the 20th of March 1944. No one spoke loudly, for everyone understood. This meeting was not about tactics, but about the limits of American technology itself. At the head of the table, Colonel Benjamin Chidlaw, head of the Fighter Projects Office, opened the meeting in a dry tone. "Gentlemen, we have engines failing across the Atlantic. We need to know why." Papers rustled, pencils tapped lightly on the map. Beside him, Dr. Samuel Heron, a British-born engine expert who had helped shape the combustion theory of propeller engines, stood, pushing his glasses up the bridge of his nose. His first sentence cut through the air. "Air-cooled engines have reached their limit," Heron explained with cold numbers. Compression ratio, 6, 65 to 1, cylinder head, temperature, limit 500 degrees Fahrenheit, combustion chamber pressure, 800 pounds per square inches, maximum combustion temperature 2,200 degrees Fahrenheit, peak power output 2,000 horsepower. Beyond this, metallurgy fails and thermodynamics takes over. Each value he recited sounded like a litany in the Church of Mechanics, where numbers replaced hymns and engineers bowed their heads in reverence. According to Pratt & Whitney Performance Log, February 1944, he continued, tests exceeding 2,000 HP caused detonation in less than 2 minutes. These numbers are absolute. The word absolute rang through the room like a creed. Leonard Hobbs, representing Wright Aeronautical, added, "Even with alcohol injection, manifold pressure beyond 50, 2 inHg is courting disaster." Someone took notes, and a few nodded. No one asked questions. On the wall, a power curve drawn in black ink stretched like a flat heartbeat. The higher it rose, the sharper it broke, symbolizing the threshold where metal melted and theory collapsed. Heron pointed to the peak. "Gentlemen, here lies physics. This is the end of our map." The words silenced the room for several seconds, followed by the faint scrape of chairs and quiet breaths. The atmosphere was no different from a church service, where men knelt before the map as before an altar. According to the meeting minutes, Major Harold Neely presented the inspection results of failed engines sent from Britain. Pistons punctured with holes, spark plugs burned black, cylinders split along their length, and recorded temperatures reaching 3,000 degrees Fahrenheit at hotspots. He tapped a finger on a magnified slide. Detonation damage, not mechanical, but chemical. Then he concluded, "Our engines are being pushed by desperation, not science." The sentence appeared in the official record, yet when spoken, it sounded like a confession. In the corner, Colonel Robert Harper of the Material Command clasped his hands, his voice low. "Gentlemen, this proves our caution was right. Water injection introduces too many variables." He listed them one by one: supply chain, intake pressure, risk of pre-ignition, and moisture contamination of pipelines. Each clause laid another layer of concrete over innovation, turning science into a fortress of compliance. No one interrupted, because in this system, disagreement meant danger. According to Heron's thermodynamic theorem, a young engineer read from his notebook, "Temperature beyond 2,200 degrees Fahrenheit makes any fuel unstable." He looked up, intending to ask something, but stopped when he met Harper's gaze. In that room, questions were not encouraged, for every formula had become scripture. Midway through, an engineer from Republic Aviation stood and spoke softly. "What about different alcohols? Methanol? Ethanol?" The question drifted into the air. A few pressed their lips, others bent to write. Dr. Heron replied quietly but decisively, "Theoretically, yes. Practically, no. We are not building theories. We are building airplanes." His tone bore no malice, yet the finality in it made the whole room shrink inward. In that moment, science ceased to be a journey of inquiry and became a faith resting on its own canon. "We don't challenge physics," Harper murmured. "We obey it." Eyes lowered in unison, and the scratching of pens resumed. According to the minutes of Fighter Projects Conference, the meeting lasted 5 hours and 40 minutes. When it ended, the conclusions were typed and signed by 3 men, Chidlaw, Heron, and Harper. The document contained only 12 lines, opening with the sentence, "Further pursuit of water. Injection technology is suspended until redesign." It was an administrative verdict, written like ecclesiastical law, carrying the weight of a decree. In the hallway, as the lights dimmed, the echo of leather shoes scattered across marble floors. A young officer gathered folders, the reflected glow falling upon the power curve. That curve, thought to be the boundary of science, looked instead like the lifeline of the system itself. Outside, wind brushed through bare branches, and from afar, the sound of a test engine rose a prayer of steel and fire. As the officers left the room, at a small corner near the end of the table, one young engineer remained seated. He had spoken no words during the meeting, nor signed the report, but stared at the sheet filled with numbers. The values: 6, 65 to 1, 500 degrees Fahrenheit, 800 pounds per square inches, 2,000, 200 degrees Fahrenheit, 2,000 HP were underlined and circled, as if each number hid a small lie. He wrote in the margin, "If these are limits, who decided they must stay?" According to the memoir of Frank Walker, the young engineer was himself, then working at the Pratt & Whitney laboratory in Connecticut. While his superiors met, he followed via telegram, reading each line of the transmitted conclusion: water injection program suspended. In a room lit by dim neon, he looked at test tubes containing methanol, ethanol, and isopropyl, three substances quietly reacting differently under the same flame. To Walker, that small difference was a reminder that no limit is ever absolute. The scene at Wright Field ended like the sealing of a creed. Science, instead of advancing through doubt, bowed before its own tables of values as doctrine. The men in uniform departed in silence, believing they had saved industry from disaster, unaware they had canonized stagnation. At the same time, in Connecticut, a single light remained on. On the lab bench, Walker placed 3 glass beakers side by side, the alcohol vapors mingling with the white glow. He noted each small reaction, each pressure and temperature figure. Outside, the snow was melting, and in the chill, he whispered a line later found in his notebook. "Numbers don't lie, but sometimes the men who read them do." The room was silent, broken only by the drip of liquid into a glass gauge. At Wright Field, the report had been sent. In Connecticut, the first question had been written. A system had just closed its door, while elsewhere, a man began to tap at the lock, and somewhere between those two sounds, the next war of numbers began. During the days when memoranda from Wright Field still flew back and forth between departments, Frank Walker, a young engineer at Pratt & Whitney, sat in the laboratory at East Hartford, Connecticut, surrounded by rows of test tubes and smooth metal plates. Outside, the melting snow revealed the cold concrete ground, where puddles reflected the fluorescent light. At the center of the laboratory bench stood 3 glass beakers, each containing a clear liquid labeled methanol, 133, ethanol, 129, and water, distilled. He called them the quiet rebels, silent insurgents in a world where formulas had been sealed. According to Pratt & Whitney Chemical Division log, March 1944, Walker had been assigned to verify the properties of the isopropyl alcohol mixture used in the anti-detonation injection system. But instead of repeating the procedure, he chose to alter the variables. He tested methanol, an alcohol with an octane rating of 133, and noticed a difference. When burned at 2,200 degrees Fahrenheit, methanol did not amplify combustion but absorbed heat, lowering the surrounding temperature by about 40 degrees Fahrenheit compared to ethanol. In his notebook, he wrote a short line, "It doesn't burn. It steals the fire." Ethanol, with a rating of 129, reacted more slowly but remained stable under high pressure. Distilled water, by contrast, did not burn at all, yet absorbed energy so rapidly that it halted the chain reaction of explosions. When the 3 substances were mixed in a 50/50 ratio of methanol to water, the result was a cold reaction temperature decreased instead of rising. In theoretical models, it was a paradox, for at the university, they had taught that all fuels must burn to produce power. Walker looked up at the trace of white vapor streaming from the mouth of the test tube and murmured a sentence he would repeat in many later lectures. "Sometimes, survival is not about burning brighter, but cooling faster." From the laboratory's perspective, it was a small observation, but to him, it was as if a door had opened to a new kind of alchemy, where molecules refused to obey human orders. According to the Pratt & Whitney internal memo dated the 21st of March 1944, he submitted a report tentatively titled Methanol-Water Equilibrium in High-Compression Combustion. The report was only 4 handwritten pages, signed F.W. in the lower corner. When it reached the desk of Leonard Hobbs, technical director, it was stamped experimental only, not for operational consideration. A dry red ink mark covered Walker's first effort entirely. The technical advisors of the Army Air Force's Engineering Division reviewed the record and returned it with the comment, "Unrealistic, unstable, unnecessary." Those 3 words echoed in every meeting like a mantra defending the system against change. Walker knew that none of them truly understood the chemical problem. They viewed everything through the lens of linear thermodynamics, while the reactions of methanol and water occurred at the molecular level, where theory surrendered. In the lab, he began conducting unofficial experiments. By attaching thermal sensors to a small combustion chamber model, he obtained results beyond expectation. When a 50/50 methanol water mixture was injected into hot airflow at 65 inHg, cylinder wall temperature dropped by an average of 70 degrees Fahrenheit within 2 seconds, with no sign of detonation. In comparison, using isopropyl alcohol caused pre-ignition at 53 inHg, with temperature fluctuations of plus or minus 180 degrees Fahrenheit. That meant, chemically, the current anti-detonation system was triggering the very phenomenon it was designed to prevent. According to the internal log fuel division num 47D10, the results were deemed deviations from safety criteria. But Walker continued. He tore off the lab's recording board and added new sheets of paper, each bearing a formula. Methanol absorbs 1.2 times more latent heat than isopropyl. Water vapor expansion reduces cylinder pressure by 15% at the detonation point. The combined mixture creates a controlled quench zone inside the combustion chamber. Those lines, scrawled in pencil and fading at the edges, would later form the foundation for the complete redesign of the fuel injection system. At night, when his colleagues had gone, Walker stayed behind, listening to the faint sound of engine tests in the distance, mingling with the scent of oil and alcohol. He recalled the meeting at Wright Field, where numbers were recited as gospel: 6, 65-1 compression, 500 degrees Fahrenheit, 800 pounds per square inches. All correct, yet those who read them believed that what was true yesterday would remain true forever. He placed his hand on the smooth, cold metal surface of the bench, feeling like he was touching the skin of a sleeping machine. If numbers are religion, he thought, then chemistry must be heresy. That sentence would later be found in his lab notebook dated the 21st of March 1944, beside a sketch of a combustion chamber labelled Water, the unburning element. In it, he described water as the silent saviour of metal. Water did not fight fire with strength, but by embracing it, absorbing it until the flame exhausted itself. To him, it was the most beautiful paradox of war, the weakest element saving the strongest. According to his colleague Bill Claus from the test department, Walker was not one for long arguments. He presented data, was dismissed, then returned to his bench and quietly conducted another experiment. Claus recalled. He didn't argue, he measured. Perhaps that attitude unsettled his superiors. While they defended theory with minutes and memos, he defended truth with measurement. 4 days later, Walker prepared to send his second proposal, this time with a new note: combustion suppression through latent heat absorption, potential 30% increase in safe manifold pressure. If correct, it meant the R2800 engine could reach 2,800 HP without detonation. But the record was never officially transmitted. The internal review board demanded further verification, which meant indefinite suspension. That night, Walker wrote in his diary, "They fear what is not in the tables." He closed the notebook, turned off the light, and looked through the frost-covered window. Somewhere outside, engines were starting up for the next test run. A flash of blue flame flickered in the darkness like a candle in a cathedral of steel. He murmured, "Every system needs its heretic." In the final days of March, while telegrams from England still reported mass R2800 engine failures, Walker quietly sent a copy of his notes to Claus. The letter contained only 2 lines. "Try this. It won't burn you." A week later, Claus brought it to the test aircraft at RAF Steeple Morden, where the engines themselves would answer in place of theory. And in that small room in Connecticut, Walker sat silently, staring at the last test tube. Under the yellow light, the droplet trembled before cooling completely. In a world burning with war, he found salvation in a reaction that reduced heat. To him, it was no longer an experiment, but a belief, a heretical faith strong enough to change the speed of the sky. Before moving to the next part, if this story speaks to you, please like and share it so more people can see. Leave a comment below. Your voice is the motivation for us to create more stories worth hearing. At the end of March, 1944, cold wind swept across the runway of RAF Steeple Morden, carrying the scent of fuel and burned steel. Inside the domed hangars, the sound of hammers striking metal echoed rhythmically, mixed with brief laughter from the mechanics. They were repairing the P-47 Thunderbolts that had barely escaped engine disasters. In a shadowed corner, Bill Claus, a young engineer from Pratt & Whitney, entered carrying a canvas satchel containing several test tubes, a glass bottle labelled methanol 99%, and a canister of distilled water. Beside him, Master Sergeant Mike Quirk, who had witnessed dozens of R-2800 engines burn out, pulled the hangar door nearly shut and whispered, "If we're caught, they'll ground us for life." Claus replied softly, "If we don't, we'll lose the war sooner." According to Maintenance Log 56th Fighter Group, the 28th of March 1944, Claus arrived at Steeple Morden under inspection order. But in truth, his mission existed on no paperwork. They selected Francis Gabreski's P-47, still grounded after the Battle of March 15. The auxiliary fuel tank behind the cockpit remained filled with isopropyl alcohol, the same mixture that had destroyed hundreds of engines in the past 2 weeks. Claus signalled Quirk to drain the tank completely and replace it with 15 gallons of a 50/50 mixture of methanol and distilled water, poured from an old aluminum can that had once held propeller cleaning fluid. In his private journal, Claus wrote a brief note: 15 gallons, 50/50, test 01, secrecy mandatory. That was a night erased from official history, for no one wanted to record an experiment conducted in direct violation of Army Air Force's technical command orders. On a metal table, Claus spread out a diagram of the R-2800 combustion chamber, donned gloves, and wiped the fuel lines with methanol-soaked cloth. Quirk looked over his shoulder and muttered, "You really think this will work?" Claus said nothing, merely pointing at Frank Walker's note. "It cools instead of burns." The next morning, as the squadron prepared for engine tests, no one knew that one of the P-47 seconds in line carried an illegal formula. Gabreski sat in the cockpit, eyes fixed on the dials, hand on the injection switch. From the ground, Quirk raised a single finger, the signal for readiness. The R-2800 double wasp engine roared to life, first coarse and heavy, then settling into a deep, steady thunder. Manifold pressure climbed past 52 inHg, then 56, and stabilized at 68 inHg. There was no vibration, no knocking. The cylinder head temperature gauge, instead of rising, dropped about 70 degrees Fahrenheit below the standard level. Claus watched silently as the RPM needle rose to 2,800 revolutions per minute, the ground trembling beneath his feet. He bent over his notebook and wrote, "Engine stable at 2,800 horsepower, smooth acceleration. No detonation observed." According to a field note by Sergeant Quirk, the 29th of March 1944, the test lasted 7 minutes. When Gabreski pushed the throttle to full, the engine's deep, even growl filled the air, like the breath of an awakened beast. There was no sputter, no smoke. The sound made Quirk exclaim, "It's singing." Claus smiled and replied, "That's the sound of numbers being proven wrong." 2 days later, they conducted a secret flight test. Major David Schilling, a renowned test pilot in the group, was chosen. On the morning of the 3rd of April 1944, the sky over Cambridge was clear and still. Schilling climbed into the cockpit of the P-47, carrying the new mixture, temporarily designated MWX-1. The plane took off at 9:32, and according to Flight Log 56th FG, reached 30,000 feet in just 7 minutes, more than 2 minutes faster than usual. He activated the injection switch and pushed the throttle to maximum. Manifold pressure held steady at 68 inHg. Climb rate reached 3,800 feet per minute, level speed 480 miles per hour, and every gauge temperature, oil, RPM, remained within the green zone. From the ground, Claus and Quirk watched through binoculars, hearing Schilling's voice over the radio. "It feels different, stronger, cleaner, like the engine wants to live." The sentence was later recorded in the Test Transmission Archive, RAF Steeple Morden, 1944. Though the signal was slightly distorted by atmospheric interference, it was clear enough to reveal that something extraordinary was happening. When Schilling landed, the engine continued to run smoothly, with no need for cooling idle. Claus placed his hand on the cylinder casing and felt the even warmth, no hotspots. On the inspection sheet, the temperature entry read, head temp drop, negative 65 degrees Fahrenheit compared to baseline. The result exceeded every expectation. All thermodynamic equations predicted that an alcohol-water mixture would reduce efficiency due to lower energy density, yet in reality, it produced 2,800 horsepower, over 40% above the theoretical limit of the R2800. No computational model could explain the phenomenon. According to Engineering Memo No. E414, observed power increase not consistent with established chemical or thermodynamic law. The sentence was typed in machine script, but anyone reading it could sense both astonishment and unease within its lines. That afternoon, Claus, Quirk and Gabreski sat in the hangar, drinking cold coffee, staring at the still warm engine. Gabreski said slowly, "We just rewrote physics, didn't we?" Claus shook his head. "No, we just reminded them to listen." In Quirk's notebook, the final entry for April 3 read, "Engine sings steady at 2,800 HP. The machine obeys chemistry, not fear." Walker's formula had now left the laboratory. In the internal memo of Fighter Command, 8th Air Force, the experiment was summarized as unofficial field result, pending review. But in practice, word spread faster than any telegram. The mechanics at Steeple Morden began whispering about the magic mix. One man tried blending a few gallons in an empty tank. Another asked for the formula. Within 2 days, 7 more P-47 seconds were secretly fueled with the 50/50 methanol water mixture, all showing identical results. That evening, Quirk made his rounds, listening to the engines running steadily like heartbeats. He remembered the nights of March, when engines had screamed and died, and found in this sound a strange kind of solace. Claus stood beside him and said quietly, "We broke the rule, but saved the engine." The words felt like an oath spoken by engineers who dared to trust experiment over command. Alchemy had become reality. In the whisper of wind through the hangar, they heard that sound again, round, steady, deep as a hymn of metal. They did not know whether their superiors would ever accept these results. But at that moment, all three understood. The mixture had saved not only the machines, but the belief that the system could still correct itself. And that night, as the P-47 cooled under the dim lights of the hangar, the engine still whispered its hymn, a quiet confession from steel to man, that rebellion, once proven right, is no crime at all. On the morning of the 8th of April 1944, a mist hung over RAF Steeple Morden as 48 P-47D Thunderbolts of the 56th Fighter Group prepared to escort B-24 Liberators to Brunswick, Germany, under the threat of Luftwaffe Unit JG-11. Though orders banned water injection use, Bill Claus's log noted, "All 48 aircraft converted, methanol, water 50/50, 15 gallons each." The mechanics had secretly completed the upgrade Walker's mix. Colonel Zemke approved the flight roster without acknowledging the modification. Officially, everything was standard. Unofficially, they were risking court-martial. According to Mission Report number 2115, the formation took off at 8:20. The B-24 seconds flew at 20,000 feet on a 300-mile route. Near Brunswick, 20 FW-190 Amperes fighters descended from 30,000 feet. At that altitude, the P-47 seconds limitations heavy, slow, altitude loss were fatal. Captain Robert Johnson, leading the red flight, waited for Zemke's signal. Then, despite standing orders, he flipped the injection switch. As recorded in his combat log, the methanol water injection pushed manifold pressure to 68 inHg, with power spiking to 2,800 HP. The P-47 climbed 3,000 feet in 30 seconds. Others followed, transforming the squadron into a wall of steel. At 25,000 feet, Johnson downed a JG-11 FWO 190 at 560 miles per hour, exceeding design limits. According to the 8th Air Force after-action report, the 18-minute dogfight saw 11 FWON 190 seconds destroyed, with no Thunderbolts lost, no engine failures, and no overheating. On return, Claus and Quirk inspected engines' temperatures stable at 430 degrees Fahrenheit, 70 degrees Fahrenheit lower than usual. In the report, technical notes stated, all systems performed within standard parameters. There was no mention of methanol. The truth was buried under the word standard. Luftwaffe HQ dismissed JG-11's report of impossible P-47 performance as exaggeration. But within the 56th Fighter Group, everyone knew, according to Operations Summary, 5 hours 10 minutes flight time, 72% ammo usage, and fuel for 30 more minutes, numbers impossible before. Zemke's comment, engines performed better than expected. That evening, Claus said, they'll call it a miracle. Gabreski replied, no, they'll call it normal. As the flashlight beam danced across a soot-marked fuselage, the truth shimmered evidence of being right before being allowed to be. Data spread quietly. Engineers adopted the standard formula unofficially. The April 1944 engine service bulletin ended with, continue current configuration until further notice. The victory at Brunswick wasn't from orders, but from quiet defiance believing results over rules. And that night, the system survived by pretending it had never been wrong. When the report from Brunswick was transmitted to headquarters on the night of the 8th of April 1944, the teletype network of the 8th Air Force clattered steadily in the signal room at Wright Field. On a strip of white paper, a short line appeared. 0 engine failures. Mission success. Recommend full continuation. The message was time, stamped 2,100 hours, sent from RAF Steeple Morden to the technical offices at East Hartford, Wright Aeronautical and Shell Oil Corporation. Those 7 words were enough to trigger one of the largest industrial transformations since the war began. According to Air Technical Service Bulletin 1944, the absence of any engine failure after a high-intensity combat mission was considered an event unprecedented in aviation history. Engineers at Pratt & Whitney read the report in disbelief. For 2 years, the R2800 engine had stood as the symbol of mechanical limitation, and now that very limit had been surpassed by a formula born in a prohibited laboratory. The next morning, the conference room at East Hartford was packed. Leonard Hobbs stepped to the board and chalked the words, methanol, water 50/50. Beneath it, he drew the new power curve, one that rose beyond 2,800 horsepower without destroying the cylinders. Gentlemen, he said, physics has been rewritten. Within the week, Pratt & Whitney partnered with Shell Oil to establish mass production lines. The main East Hartford plant converted part of its aviation fuel line to produce the methanol water 50/50 mixture with an output of 10,000 gallons per day. Large steel tanks were welded, fitted with pressure valves and distribution pipelines. According to the U.S. Army Fuel Supply Division report, the new mixture could supply the entire British-based fighter fleet within 3 days. From the ports of Liverpool and Bristol, supply ships carrying steel drums marked MW Mix were dispatched directly to forward airfields. At the technical level, testing resumed. Mechanical teams at Debden, Boxted and Lyon inspected 200 R2800 engines after 1 week of using the new mixture. The results were consistent. Cylinder head temperatures dropped 570 degrees Fahrenheit, manifold pressure stabilized at 68 inHg, and power was sustained at 2,800 HP for more than 10 minutes with no signs of detonation. These findings were confirmed by the 8th Air Force Engineering Summary, May 1944, with a closing note, field results consistent with laboratory data by F. Walker. From a strategic perspective, the impact of the discovery spread faster than the aircraft themselves. Within a month, the U.S. Air Force's loss rate fell 37%, while the Luftwaffe lost an additional 52% of its fighters in direct engagements. The Operations Statistics Branch reported, mission aborts due to mechanical failures is approximately equal to 0%. The engineering system that had once collapsed under rigidity now revived through the self-correction of those it had once constrained. The earlier memoranda that declared the R-2800 to have reached its physical limit were recalled and amended. A new annotation appeared. Revised upper limit, pending further field validation. According to Frank Walker's account, when he was summoned to Wright Field at the end of April, the first printed copy of the methanol water formula was framed and hung in the conference room. He walked in among the same men who had once dismissed his report, listening as they discussed molecular stability and storage safety. A young officer asked, "Sir, did you expect this outcome?" Walker replied, "No. I expected the system to resist. It surprised me that it learned." The answer silenced the room. In the history of industry, few mistakes have ever been acknowledged with such respect. At the East Hartford plant, the methanol water production lines ran around the clock, the sounds of relief valves, pressure pumps, and the whistles marking each completed batch merged into the industrial music of a new age. The first containers were labeled Approved Fuel Additive, Type MW, and bore the inspection seal of the U.S. Army Ordnance. On the label was a small line of print, manufactured under Walker process. A name absent from textbooks, yet it had become a new chapter of applied physics. Reports from the European front in May and June confirmed the superior performance. The P-47 Thunderbolt reached a maximum speed of 470 miles per hour at 25,000 feet, an average increase of 45 miles per hour over the previous configuration. Pilots reported engines that were smooth, responsive, cool under pressure. Maintenance records showed cylinder lifespan rising 28% and oil consumption dropping 15%. Each figure stood as evidence that when forced to face results directly, the system chose adaptation over resistance. In post-campaign technical conferences, officers described the phenomenon with the phrase, "from bottom-up correction, a reform beginning at the lowest level of the system, then spreading upward." No one dared call it rebellion, though in essence it was how a machine relearned to survive. The strategic maps hanging in command offices now featured a new curve, the true power graph of the R-2800. That curve rose beyond the old limit, like a widening crack in the glass of belief, letting in the light of experiment. In Walker's notebook, he wrote an unusual line. "Alchemy is not turning lead to gold, it's turning failure into purpose." To him, true alchemy was not about seeking gold, but about rediscovering a reason to believe in the system itself. The methanol water event had not only saved the engines, it had restored to science, a quality lost in war. The humility to admit that every law exists only until someone dares to cross its line. After the war, the discovery of the methanol water 50/50 mixture quickly influenced engine technology. Engineers shifted experimentation toward turbines and jet propulsion, basing their designs on the principle of combustion chamber cooling through molecular reactions, laying the groundwork for rocket fuels and cryogenic propellants. American laboratories combined battlefield data with research to refine fuel injection and thermal control systems. Germany introduced the MW50 system under the same concept, but limited production capacity prevented it from gaining a strategic advantage. In the United States, the East Hartford facility established a production line, manufacturing 10,000 gallons per day, distributing it to forward bases to ensure supply and expand application on a large scale. This efficient supply chain was the decisive factor that turned a laboratory invention into a combat standard. The more significant legacy was a change in organizational thinking. Frank Walker forced the system to acknowledge that a scientific model is not an immutable truth, but a framework that must be continuously tested. He did not reject physics. He emphasized that when empirical data contradict theory, the model must be revised. This lesson was incorporated into post-war engineering curricula and maintenance protocols. On a cultural level, the story became a symbol of experimental spirit and professional courage. The clandestine actions of mechanics and engineers demonstrated that innovation often arises from practice, not from conferences. Brunswick and Steeple Morden were cited as proof that experimentation under extreme conditions could transform an entire system. Ultimately, the legacy of the molecular rebellion is a reminder that an organization's ability to correct itself is more vital than its reverence for numbers. A single drop of water in the right mixture can prevent catastrophe, and sometimes the smallest act decides the direction of history. Thank you for following this journey to its end, where one small idea could alter the laws of war. Every story is a fragment of memory from those who dared to try, to fail, and to begin again. We are committed to bringing you the finest content, recreating the moments that history wrote in sweat, smoke, and steel. Don't forget to subscribe to the channel to follow more battles,